Hello again, all. 'Tis me. I'm back. I want to talk more about stuff, just because it's almost like science fiction is becoming fiction now. So any big old Trekkies out there surely must be as excited as I am that some of this stuff is clearly coming out. It's clearly real and possible, as discussed in previous videos. So this subject, as I mentioned, is time. Time. It's a funny old mistress, is time. Um, it's probably not what you think time is. And as I said before, I'm approaching this from a layman's point of view, as in a guy who's not a scientist, not a physicist, um, not a mathematician, just someone with a passion to learn about this stuff and read the theories. I don't think there's any reason. I mean, there are theorists who can't do maths, but I'm just someone who loves this, and I think everyone should love this, and I think it should be standard everywhere because of the fact humanity is growing up now. Finally, I think we're growing up, and I think everyone's getting on board with fuck this shit. We need to change something. Let's do stuff that's going to make life way more fun. I'm all about fun. So I want to talk to you about time. I'll probably change your perspective about what time is. If you haven't discussed time before, have you got the time to discuss time? Oh, it's a paradox. So let's go. Let's delve into it. I've prepped some bits and bobs to show you. First off, I've got to remove my face. So first thing you need to be made aware of, which is going to start the change of your opinion or perspective on time, is you may have heard the word space-time. Not space-time, space-time. Not space-time, space, pause, time, space-time. It's one word, because it's one thing. Space and time are one thing, thanks to old Alberto. We now know that it's not true, that time is a relentless thing. It just keeps passing through seconds, minutes, hours, days, months, weeks, fucking years, millenniums, centuries. It just keeps on going, doesn't change. But we know that's not true, thanks to old Einstein. He turned up to a press conference. He's leaned over and gone, "Mate, that is not true." And he's legged it. He's done, left you with that. But it's not true. Time can be changed, warped, bent, slowed down. I'm not sure if it can be sped up. I've never asked that question until I thought of it then. Because apparently, as far as I'm aware, relativity in physics terms and mathematical terms can be reversed. What applies one way applies the other way. So if you can go forward in time, you can go backward in time. We know we can go forward in time, but we don't know how to go backward in time. Again, even if it's possible, but almost everything Einstein predicted with his theory has been proven to be true. The last thing being gravitational waves. We're like, are they real? Turns out, yes, they're fucking real. Loud ass plane. So here we are, we're on our graph, very simple. So on the upper, the y-axis, the vertical axis, we've got space. And on the, it's like I'm telling you like you can't see. I mean, might not be able to see, that would be rude, shut up now. And then on the x-axis, we've got time, from left to right is time. While you and I are sitting on our arse doing fuck all, in front of our monitors or in front of our phones or tablets, whatever, or TVs, I don't know. We're not moving at all in space. We're sitting down. We actually are. That's relativity, but we'll get to that in a little bit for more fun. So time, we're moving at the moment by doing fuck all. We are moving at the speed of light, believe it or not, in time. We are only moving in time. We are sitting here progressing by the second through time. We're not moving through space. If you start to move quicker and quicker and quicker and quicker, and let's say you could get to 50% of the speed of light, which would be what, 335 million miles an hour. This graph would change from you directly going left to right in time only to looking like that. You've now got momentum. You are moving not only now in time, you're also moving in space. But the wonder of this graph is it clearly shows you if you're moving in space, you're moving less in time. When we were here, we're directly moving in time. Nothing's changed in our trajectory. You're going straight fucking forward through time. But if you add speed, you're no longer just moving in time, you're moving less in time, and you're moving some in space. So let's take that to the extreme and say we're going to move, this line being us, we're now going to move in our little seats at the speed of light whilst continuing to watch this video. We're moving now at the speed of light. Again, we know that's impossible. You need to be infinitely heavy, well, you will be infinitely heavy, and you need infinite energy. It's impossible, but for argument's sake, let's pretend we can. Einstein can do it, we can do it. Thought experiments. So let's say we now move in space at the speed of light. Well, then the graph looks like this. Excuse me, it's total reversal. You're no longer moving in time at all. You are only moving in space at the speed of light. So it clearly shows you time is a weird thing. It's connected to space, the medium that we move through. It is the same thing. It's space-time. And just to reiterate, when we're not moving at all, we're only moving in time. But when we're moving quick, we're only moving like light speed. We're only moving in space. We're not moving in time. So that's a way to stop time, really. Just stop it for a bit. If you can go at the speed of light, which you fucking can't, you wouldn't experience time anymore. I've no idea what the ramifications of that are, and I still have many questions about that. But as of my understanding of space-time, this is what it means. You're not moving in time when you're moving at the speed of light, space. So now I can point you to the experiment that proved this theory to be true. It's called time dilation, or the Lorentz factor. And the Lorentz factor being how much is an object affected, not only physically, and but how much speed and momentum, but also physically, how much is this affected by moving really, really fucking fast. And again, that's the Lorentz factor, which is the equation that tells you the effects this time dilation will have on a moving object. So I'm just going to go with something I prepared a little earlier, guys. Okay, but I opened up the wrong Photoshop, so I'm just going to stop that when it eventually opens. So here we go. This is the experiment. It's called the Hafele. Oh, I need to double check. Hafele. I don't know how to pronounce it. It's like the Scottish people trying to say burglar alarm. Get a Scottish person to try and say purple burglar alarm. Purple burglar alarm. Purple burglar alarm. It's hilarious. Anyway, stop winding up the Scottish now. So this is an atomic clock. A very simple version of an atomic clock. It is the most exact way to tell the time. There is also the universal candle, which, as I believe, is supernovas, which is also a very exact thing, and they can measure distance using these, but that's cosmological, not quantum mechanical. So atomic clock, it's two mirrors, one at the top, one at the bottom, and in the middle they drop an atom, right? And the atom is going to bounce up with my bad arrow, and it's going to bounce down, and it's going to do this indefinitely. It's got some initial momentum which causes it to bounce, and I believe if these are perfect mirrors, it won't ever lose energy. It's like perpetual motion. It's never going to stop going. But clearly, being an atom, it's going fucking super quick. So I don't know how they quantize how many would relate to a second or equate to a second, but for argument's sake, let's just say, chill out. Let's just say this goes up 1,000,000 times. When it's gone up and down 1,000,000 times, it sounds like a lot, but it's fucking small. When it's gone up 1,000,000 times, we count that as 1 second. So that's this atomic clock. This atomic clock, we're going to keep here. Mine's here, yours is next to you. It's not moving. It is, but we'll talk about that in a minute when we get to relativity. So this is bouncing up and down like this. 1,000,000 of them, we get a second. So in fact, let me write that. 1 mil equals 1 sec, in case I forget what I said. So 1,000,000 equals 1 second. 1,000,000 up and downs, both together, 1 second. But what if the mirrors were moving? And this shows you it in stages. If you were to take still frames of this box, this atomic clock box going real fast, and you could take still frames, this is what it would look like. Excuse me. And the Keating experiment, what they did is they kept these, I don't remember if I already said this, but I'm going to repeat anyway. So they keep atomic clocks on the ground, not moving. Mine's here, yours is there, it's not fucking moving. Relative to you and I, they're not moving. But they sent 4 on the plane, on planes, 4 planes, 2 going east, 2 going west, around the world twice. And what they wanted to do was to compare the Lorentz factor that they wanted to find out, or they'd theorized would affect these atomic clocks. Once they brought these 4 clocks off the planes back to Earth, compared them to the ones that had never moved from the Earth or their position, there was a minuscule difference, a delay between them. It's small because it was only going about 600 miles an hour, 700 miles an hour. It's not like they were going anywhere near the speed of light. So it's a very small difference, but it's significant enough to be able to prove the theory true. There's just cats everywhere kicking off. Is it the day I'm waiting for the birds to fly overhead now? Jesus, he's loud. He's loud. I'll talk through him. He's so rude. Archie, you're so rude. Do you mind? Yeah, thanks. Do you mind, Archie? Oh, he's not stopping. Archie, do me a favour, shut up, will you? Yes, you. Don't look at me like that. Look at him. No, I'm not going to move that. Get on with it. I don't know if I'm going to cut that. Anyway, so this is now moving. These are the still shots of those things moving. When they come back together, they did not match. The ones that had been moving around the planet on the aeroplanes were slower than the ones that were on. They were slower than the ones that were on the planet. The ones that were on the planet were quicker. Time ran faster on the planet than they did on the aeroplanes that were moving fast around the planet. I don't know, I'm trying to figure out if I confuse myself with that, so let me just repeat that. The atomic clocks that stayed still, static, no movement on the planet like yours and mine, they were marginally quicker than the ones that had been around the world, the 4 that had been around the world. The ones on the planet and on the ground matched each other perfectly well, I'm pretty sure. But and the ones on the planes matched each other too, perfectly well. But they didn't match with each other. The moving ones and the stationary ones did not match. The ones that were stationary moved quicker than the ones that weren't, the ones that were on the planes. And I'll show you exactly why that happens, and then logically it makes complete sense why that would happen. So again, as I said, we've got still shots of this of this atomic clock box moving very fast. Let's say it's going from left to right. I don't know if that mirrors, whatever. So let's say we've got an atom here on its bottom bounce. It's just hit the bottom mirror. If it bounces straight back up, the top mirror is not going to be there anymore. Again, if you imagine this is moving like this, once it's here and the mirror's here, the atom is at the bottom. As it bounces off the bottom, because it's moving, the top mirror is going to be over here now, because if it goes straight back up, the mirror's not there anymore, it's moved. So it can't go straight back up. It's got to do this. It's got to bounce on the bottom mirror, travel to here, bounce on that one, travel to here, bounce on that one, and so forth. So it becomes abundantly clear and perfectly logical that this atom is having to move further than this atom, which means it takes longer in between each bounce. And we can, in fact, if we cut these, that might make it a bit simpler for me as well to look at. So imagine that This is just the box. This is the position of the same lower and upper mirror as it's moving. One's going to be here as it moves. By the time it hits the top mirror, it's going to be over here. So again, you can see clearly that by going from here to here to here to here, this length is much longer than the length just going up and down here. From this to here is less of a distance. From here, damn it, from this point to this point is less of a distance as of compared to this point to this point. So that proves that time will tick slower the faster you move. And again, the time dilation is going to be massively significant the closer to the speed of light you get, which is why purely based on speed, you can travel into the future. Just go real fucking quick, because you can see now, the faster you're going, the less you're experiencing time. As I say, there's a twin paradox about two twins going out. One stays on the planet, one goes off, the speed of light comes back. They're different ages. That's what that means. And when I said I was going to talk about relativity, or relative, to the persons on the plane, the people on the plane looking at their atomic clock on those 4 planes, you've got the passenger, they're looking at their clock, making sure the experience is running perfectly well. And to them, it's going up and down. It's not moving anywhere. It's just up and down. So they're confirming, yeah, our atomic clock is working perfectly well. But to the observer on the ground, if it was possible to, slow up a plane going past so you could actually look at the atomic clock. But again, from their perspective, it's just going up and down because they're going at the same speed. It's relative to them. To me, looking at the plane, the atom isn't going up and down. It can't possibly be going up and down. It has to be doing this pattern here. It's got to be going don't, because it's moving with it. So that's where the idea of relativity from the famous theory comes from. It's relative. The clock, relative to the people on the plane, is going up and down. Relative to the people on the ground, it's going diagonally, which is crazy. And again, I've mentioned it before, your sat-nav works because of this time dilation. If they hadn't factored this in, your sat-nav would probably be about 5, 6, 7 miles off, because it has to factor in that time up there is moving quicker than it is down here. So it's moving slower than it is down here, because we're stationary, but those are moving around pretty fucking sharpish. So that shows how it's possible for time to slow down. I've only got 2 minutes. I wanted to show you one other thing before I bugger off, because I had this set up, so I might as well use it, you know what I mean? So this, when I said the word space-time, this is what I mean. That this, you can picture this block here as a 2D slice of space. Of course it's 3D, but it's a 2D slice. And here is a massive, bare, heavy object, the sun. If there was sufficient tension on this flat plane, the sun would just sit on it, wouldn't really change anything around it. It just, sit on the top like it was on the top of a table. But space doesn't do that. And this is partially confusing still to me. What space does is, let me just check my thing. Yeah, when there is a heavy object sitting in space, it does this. It doesn't do that. I've got nothing selected. Hang on. No, right, okay, bear with me. Let's just take that. Kind of looks central. And that doesn't look like a sphere. Anyway, shut up, Nick. Get on with it. So, with a heavy object, this 2D flat space ends up, I'm going to get this right in a second, ends up doing this. So it's now bending and warping around the heavy ass object. So this sun is causing, and again remember this is all round, it's causing the space to warp around it. So time is following the same, because it's the same thing. Space-time. What is that? Stingray. So if you're traveling around here and then suddenly you're following this dip, not only are you going to speed up towards the central because you're being pulled towards it now, But time is also being stretched towards it too, so it's being slowed down. So again, the heavier this object is, the more warping. And if it was a black hole, seriously, a black hole, which I'll do a video on because I think they're brilliant, kind of looks like that. Yeah, it's pretty dire. What a black hole does, it pretty much does this. It's hideously scary, but it does. And again, so that's how space-time is connected, how it's the same thing, how time can be affected by the speed you're going if you're close to a heavier object. So in terms of going into the future, either go real quick or get close to something real big, which in turn means you've got to go real quick. If you want to go around a black hole, the most gravitational, crazy ass thing in the universe, if you want to go around one of them, you've got to go fucking quick because that shit draws in light. So orbit a black hole for a bit, come back, you're in the future. I think I've covered everything. All right, I know it was a little bit longer, but I'm done now. All right, sweet. Yeah, there'll be more because I'm enjoying this. I hope you are too. I hope you're getting some shit, getting some excitement from this like I do. Anyway, just procrastinating.